In this video, we're going to do an example using our new rules and solve this tangent line problem. And then we're also going to look at a technique to help us find derivatives. That's very useful. So first, the example problem. We want to find the equation of the tangent line of the function y equals the sine of x minus 2 at x equals pi over 6. Now, normally you don't have to graph these. Sometimes it's good to graph them, but we're going to go ahead and graph this one just to get a visual of what we're looking for. Alright, so the sine of x minus 2, let's see, that's down 2 units. 1, 2. And then here's our general sine function. Right, there we go. So that's the sine of x minus 2. And then pi over 6, that's pretty close to here, so it's probably about right there. And here is our tangent line. So we're looking for the equation of this tangent. What is that line? Now, if you remember, we need two things before we can write the equation of a line. We need a point, and we need a slope. Okay. Now at this moment, we don't have either of them, but we have this information. We have the equation and where the x value is. And when you're given the x value, to get the point, we just substitute in that x value. So that means y of pi over 6 is going to be the sine of pi over 6 minus 2. Okay, so we do have to remember our unit circle. The sine of pi over 6 is 1/2 minus 2. So this ends up being a negative 3/2. So our point is going to be pi over 6 negative 3/2. Now we need a slope. Right now we don't have a slope. However, we do have this new tool of calculus called the derivative. And if you remember, the derivative, in kind of a way, is going to give us an equation that allows us to find the slope of tangent lines. So if y equals the sine of x minus 2, then y prime, well, the derivative of the sine is the cosine, and the derivative of 2 is, well, 0. Okay, so then we substitute in y prime of, we substitute in pi over 6, so y prime of pi over 6 is the cosine of pi over 6, which is the square root of 3 over 2. Got to go back to that unit circle again. So the slope is the square root of 3 over 2. Okay, so we can write the equation of our tangent line. So I like to use point slope form. Y minus y1 equals m times x minus x of 1. Okay, so let's see here. We get y minus y1, so that's y plus 3/2 equals the square root of 3 over 2 times x minus pi over 6. And, well, it doesn't tell us to put it into another form, so that is it. So there is the equation for this tangent line. Right, so this is a common thing that we're going to be doing throughout this year, and that is, if you're given an equation of a function, or even not the equation of a function, but you're given an equation, and you're given an x value, can you find the slope of the tangent, the equation of the tangent line? And you can. The first step is to substitute in that x value into the function and get your y value. Then you take the derivative And inside the derivative, you put in your x value and you get the slope of the tangent line, and then you can write your equation. Okay, so let's look at what we've done so far. What we have so far for finding derivatives. We have the power rule, which is very handy. We have the constant rule. We have the constant multiple rule. We have the sum and difference rule. We have the sine rule. And we have the cosine rule. Good. And all these rules, well, these you kind of just do almost automatically. You tend to not think about it. But we do need to remember the power rule, the sine rule, and the cosine rule. We'll do this enough. We'll use those rules so much they almost become secondhand. And we'll come up with other rules. However, once in a while, we're not going to be able to have a rule to help us find the derivative. And so, when you don't have a rule, we do have a series of techniques that help us find the derivatives. And one of the most important and most effective techniques in finding derivatives is the technique of just to rewrite and simplify. Let's look at this. So this is technique number one. And that is to rewrite and simplify. So let's see what we mean by that. So let's say if y equals 3x minus 2x squared all over 7x, find y prime. Okay, so when we start off with this, we think, okay, we got y equals 3x minus 2x squared all over 7x. And as of this moment right now, there's no way for us to figure out the derivative of that. So we're thinking, well, how do we take the derivative of it? But then we remember our technique of rewrite and simplify. So watch how we rewrite this equation to make it in a much simpler form. So the first thing we're going to do is we're going to split this into two fractions. So we're going to have 3x over 7x minus 2x squared over 7x. You can split things into two fractions. That's okay, as long as you keep the common denominator. And then we can simplify things. So let's see here. 3x over 7x just becomes 3 over 7. And a negative 2x squared over 7x, well, one of the x's cancel out, so we get 2 over 7 times x. So now we have this equation, y equals 3 over 7 minus 2/7 x. This then becomes a much easier equation to take the derivative of. And so now we can find that y prime equals, well, the derivative of a constant is, that's the constant rule, derivative of a constant is 0. And then the derivative of a negative 2/7 x, well, we have the negative 2/7, we keep that out in front, and the derivative of x is 1. So we end up with a negative 2 over 7. And there we go. Let's try a couple more of these where we use our new technique. So for this example, let's say we have y equals 9 over 5x squared, and we want to find y prime. Again, we have 9 over, you see this is something that would be hard to take the derivative of. But if we do a quick rewrite, it becomes a lot easier. So we rewrite it to be y equals 9/5 times x to the negative 2. And now this function is a lot easier, or this is a lot easier to take the derivative of. I mean, it's the same function, but because we rewrote it using a negative exponent, it's a lot easier for us to take the derivative of it. So then y prime becomes, okay, the 9/5 stays out front, 9/5, and then we bring out the 2, negative 2, so you got negative 2x, and then we subtract 1, negative 3. So our derivative ends up being, let's see here, negative 2 times 9 is a negative 18 all over 5x cubed. See, not so bad. Let's do one more. This is a good one here. So for this example, if y equals 1 over the 7th root of x squared, find y prime. Okay, so here's one. I mean, even myself, I would have a hard time doing that one without rewriting. I mean, we have a 7th root in there. But again, a simple rewrite really helps things. And we do have to remember that a 7th root is same as x squared to the 1/7 power. So we do have to rewrite this to be y equals, what is it? And then it's in the denominator, so it's now a negative. So we're gonna have, I'll do this in 2 steps. 1 over x to the 2/7 power, and so y is going to be x to the negative 2/7 power. I want to be careful about that. You can do this in 1 step. You could go from here to here, but if you need to do 2 steps, that's okay. Alright, so now we can take the derivative, y prime, so we bring the negative 2/7 out front, negative 2/7 x, and we got to subtract 1, so what's that going to be, a negative 9/7? There we go. So that means y prime is going to be a negative 2 all over 7 times x to the 9/7 power. There we go. Now, if you did want to write it to be negative 2 all over 7 to the 7th root of x to the 9 power, that's okay too. But a lot of times once we take a radical and put it as a rational exponent, we tend to keep it that way. Because once we get the derivative, a lot of time we're going to use it for something, and it's easier to work with the rational exponents. Okay, so I'm stressing this right now, but I know some students will forget this. But this technique number 1 of rewriting before you simplify, it's such a powerful technique. And sometimes once we get into doing applications of derivatives, students forget it, and so they get a problem that's challenging to take the derivative, and if they would just rewrite it, it becomes so much simpler. So try to remember this technique. It really is a powerful one. It's one we use often, and if you just can kind of somehow get it into your brain that, oh, can I rewrite this first before I take the derivative, it really does help out in finding derivatives later on as we're continuing our study of calculus.